let's get started. Good afternoon, everybody. My name is Mojda Khorsan Hedman. I am the session co-chair. The chair of the session is Stephen Lowe here. We will be taking notes based on the presentation. This is the last session, and we have 4 papers to be presented. So the presenter, please introduce yourself, the university that you are from before you start the presentation, and you will have 15 minutes to present as we did on the other sessions as well. So the first presentation is with Ada Pavani. Ada, please. The floor is yours.
Thank you. Thank you for the introduction. Good afternoon, everyone. I am Ada Pavani from Federal University of ABC. The work I'm going to present is a proposal and description of a test system with wind, hydro, and fossil fuel power plants for static analysis. My co-authors are Victor Neumann. Actually, this is a result of the work of the PhD of Victor Neumann. Roman Cuyava from Federal University of Paraná. Victor is also from Federal University of Paraná in Brazil. And Professor Rodrigo Ramos from University of São Paulo. All of the authors are from Brazil. So the outline of the presentation, I'm going to present an introduction, the proposed test system, some characteristics of this proposed test system, the data structure, very fast, some application examples, and the conclusion and future works. So the increased penetration of wind power calls for the development of algorithms and methodologies to deal with several aspects of wind related to wind power. Uncertainties, need to control the voltage, voltage stability margin, a lot of problems that we have to deal with wind powers. So there are several works proposing models and solutions for static analysis for power system with high shares of wind power. And we know, that everybody that works with it know that test systems based on real systems contribute to validate these proposals. So the contribution of this work is the proposal and description of a test system based on part of the Brazilian power system. Here's some comparisons. The Brazilian power system, it has continental dimension. As we can see here, compared to the European system, we have similar dimensions, 4,000 kilometers of distance. And the Brazilian power system is composed of 4 interconnected subsystems, north-west, north, southeast, and south subsystems. They are interconnected, and it's very good for us because we are mainly based on hydropower. The installed generation mix on the Brazilian power systems is based, we have a little bit of PV. Hydro, we have 62% of hydro power, 22% of thermal, and 17% of wind. So the Brazilian power system presents now 20 gigawatts of wind power installed capacity, and around 90% of this total capacity is located northwest of the country. Actually, at northwest geographically of the country and in the northwest subsystem, as we could see in the interconnected system. So this paper proposes a test system for static analysis based on the northwest subsystem of the Brazilian power system. And this test system is composed of 30% of wind power, 31 wind farms, 58% of hydro, 19 power plants, and 29% of thermal, 18 fossil fuel-based power plants. So the Northwest region is a reference in the production of wind energy in Brazil. In the last year, approximately 89% of the energy consumed in the region came from wind power. Actually, during the months that we have more wind in Northwest region of Brazil, they export to the southwest subsystem. The high wind power penetration level requires a coordination of reactive power sources to maintain the voltage levels of the operation, for the operation of the system. The Brazilian interconnected power system, we can get this data. It's available online, but it's not in usual format that we use, especially in academic works. It presents the format that is used for the programs that we use in Brazil. That's a specific software. And the proposed test system based on the Northwest region that we are proposing here is composed of 229 buses, including transmission and the sub-transmission lines. These lines are in voltage levels of 520, 230, 138, and 20 kV. So this proposed test system is available, is online available, and the files that we have available, we have the IEEE Common Data format that we had to work a lot on that, single line diagram, and also MATLAB version using structures compatible with programs like PSAT for users of MATLAB. So the data comprehends different load levels based on the physical load behavior and typical capacity factors of the power plants. The total load of this test system is 4.70 gigawatts distributed in 42 load buses. The power exported to the other subsystems, north and southwest subsystems, is modeled as a constant load at the border bus bars of this subsystem, and the test systems adopts heavy, medium, and light load levels, which are calculated based on load measurements for different months of the year, considering the season effect. The wind farm's capacity factors are obtained from historical data as well, and they are available in the proposed test system for each month of the year, because we can have a lot of variation. And the wind farms are modeled as a PQ bus generators, but the capability curve limits are available in case of the wind farms need to be modeled as voltage-controlled buses with their operational limits. So we also have the generation costs, demand price parameters, and market constraints, which are included in the supply and demand data structures for energy market analysis. So this is just a view of the data structures for MATLAB version, which are compatible with PSAT toolbox. As we can see here, the regions of these test systems, they are basically based on the states of the Northwest region of Brazil. So I'm going to show just simple application examples here. In this case, for load flow and simulation and PV curves. For the load flow simulation, considering it as a base case, the average annual load, it results in losses of 100 megawatts. That's about 22% of the total load. So here we also present the PV curves, considering the critical bus for different operating points. So the idea is to use this system to run this kind of analysis. A very important example for us, because it was basically the result of the thesis of Victor that proposed the system, actually, that get all the data and converted it. It's, for example, it's actually one paper he published. It's that calculates the loading margin sensitivity in relation to the wind farm generation power factor for voltage preventive control, because in systems that we have a lot of wind power, usually we can have problems with voltage control. So he can. So now it's ranked the the wind farms that if we control the power factor, we have more influence on the voltage stability margin. So as we can see here, it's capable of ranking the wind farms that presents more influence on the voltage stability. So the possibility of controlling the power factor of these wind farms can result in improvement of the voltage stability margin of the system that sometimes is needed. In Brazilian grid codes, it's required that I think that is the same in other countries, that the power factor or even the voltage control at the bus of the wind farms can be controlled, and it can be required by the system operator. Another example here is actually related to the costs of the generation. So the generation cost and demand price parameters available in the test system are used or can be used for an optimal power flow routine. In this case, it's just a simple case that we show that they can be used. And we associate an optimal power flow with voltage security constraint. So the main function here is the minimization of the costs related to the generation, and with a weighting factor considering also voltage security constraints. So as we can see in this graph, if we vary the weighting factor, prioritizing the voltage stability margin. So only if the weighting factor is close to its maximum value, that's 1, the voltage security is prioritized. And when it's prioritized, it increases the output power of the thermal generators that are the most expensive in our system. So as conclusions, this test system can be used to validate methodologies to improve the operation of power systems with wind farms. As example, voltage stability, grid congestion, optimal power flow, contingency analysis. And as perspectives of these test systems, we plan to include data for dynamic analysis, data from PV power plants that are connected at this subtransmission lines in this northwest region. And we also plan to include time series of wind and solar radiance of the sites of these plants. So this system is available in this link that is also in our paper. And if someone would like to require access, please contact Victor Naumann, which is this email. Thank you very much for the attention.
Thank you very much, Ada, for taking to be on time. We can take one question. Kostas, please.
Kostas Vournas, National Technical University of Athens in Greece. Nice work, congratulations. I just want to point out a detail. Why don't you take equivalent generators for the two external systems? It would be much more, how to say, realistic than assuming that the P and Q will remain constant.
Okay, thank you, Professor Vournas. We are considering that.
Just as a follow-up and kind of an explanation, in these cases, the interconnections, they have fixed values because they are the power exports are defined by contract, so they have to be controlled to remain as constant as possible. So this is why we went for this approach as opposed to to using a generator as an equivalent. Yeah, sure.
A generator could be also a PV if you have a constraint in active power.
Okay. Thanks.
Claudio Canizares, University of Waterloo. Interesting work, I guess very practical. My question is regarding validation of this system, especially for the dynamics, because in that case, what Costas was mentioning will make a difference, right?
Yeah.
If you don't have equivalent generators of that system, the dynamics are not going to be the same. I can see that from the steady state point of view. So in that regard, do you have any validation? Can you comment on the validation?
No, I don't think we have a validation, but we can compare with simulations with the complete system. This is yeah, we are planning to do that, but Victor has finished his PhD, so we are trying to find another student to keep with this work. So this is one of our future perspectives of keeping with this work, because we plan to use this system for other simulations. Thank you for your suggestion.
Thank you very much, Ada. So our next paper is power response and modeling aspects of power electronic loads in case of voltage drops, and the presenter is Sebastian Lehmann. Please, the floor is yours.
Yeah, thank you. Do you have
Yes.
So that's... Yeah, good afternoon. My name is Sebastian Lehmann. I'm from the Technical University of Dortmund, and today I want to talk about the power response and modeling aspects of power electronic loads in case of voltage drops. So the motivation for this paper was that we see an increasing share of power electronic loads in the grid. So a survey in 2030 revealed that more than 30% of the loads in residential areas are already power electronic loads, and we can assume that 9 years later this share has increased. Power electronic loads are used for a variety of applications like LEDs, switch mode power supplies for consumer electronics, and also for ICT, and also what we see, the electric vehicle charging stations for the electric vehicles. Yes, and for short-term voltage stability here, the load dynamics are very essential. But if you look into the literature, there is a little bit of lack of suitable simulation models of these kinds of loads for these types of stability investigations. And therefore, we want to investigate how we have to model these loads, and then also how they have differences or similarities against constant PQ loads, because it is often also assumed that these types of loads are constant over a whole range of voltages. So the general structure of the paper is that we first want to determine the load dynamics by measurements in the laboratory, then derive dynamic load models and identify which are here the important aspects, and then a little demonstration of the impact on short-term voltage stability. Here you can see the laboratory setup. So on the right-hand side you see a photo, and on the bottom the respective single line diagram. For the voltage source we have a programmable three-phase power amplifiers, then we have a transformer to connect the load to the voltage source, and we have also measurements for voltage and currencies, and then we have the load itself, and here, which you can see with the internal components. On the bottom left, you can see an exemplary voltage reference signal here for a fault duration of 100 milliseconds and a voltage drop of about 60%. Next, you can see here the measured power electronic loads we selected. So we concentrated here on switch mode power supplies. Of course, there are many other power electronic loads, but we concentrated on these. They have different functionalities like battery charger, PC power supply, evaluation board, or also a DC power supply. We selected them because they have different power factor correction techniques. So without any, with passive, active, and also passive again, but then for three-phase. And you can also see that is also a little bit reflected by the rated power, because the PFC technique depends on this. What I now want to show you is the general power response of such a load under voltage drops. So we start here from the voltage drop from 20% to 100%, which is like a solid fold. We have different durations of 100 milliseconds and 160 milliseconds. And also I only show here the fundamental power. So on the top, yes, here on the top you can see the active power, and on the bottom the reactive power, and the power response can mainly be divided in 3 states. So if the voltage starts to drop, we see also a reduction in the power, which is also like a disconnection from the grid. Then during the voltage drop we see a restoration. And after the voltage drop, so at voltage recovery, we see a high power consumption due to the loading of the internal capacitances. And now if we increase the voltage drop, so here for 40%, 60, 80, and 100, we see that the power recovery is decreased, and also what we see that the power consumption at voltage recovery is greatly increased. And this is for active and reactive power. Now, if you compare this with the longer fault duration, now with 160 milliseconds, we don't see so much of a difference because the load reaches an intermediate steady state here during the voltage drop. So either it can restore its power or it stays disconnected. So this is why we focus more in the following presentation on the 100 millisecond. If we now look at the other loads, so here with passive power factor correction, in general, we see also these 3 states. But what we can see here for this particular load is that it disconnects very early, and also we have a second power reduction after the voltage recovery. For active power, we see a quite fast power restoration here, which is due to the internal boost converter, and also which is related to this boost converter stage is these slight oscillations afterwards. The 3-phase loads also in general behaves quite similar. Of course, we have here some quadratic voltage dependency of the load here during the fold, but what I want to show here is that we had some limitations of the laboratory equipment because the power amplifiers had a current limit of 30 amps, and you can see that the voltage of the power amplifiers were heavily distorted at voltage recovery due to this current limitations, and that's why we assume that this behavior at voltage recovery may not reflect the true power response. Now I want to show you the general modeling structure of these loads. So in general, the modeling structure is oriented on the general PFC circuit design. But what I also have to mention here that also these circuits are based on the former work of other researchers, which I've shown here on the bottom. But what we have added here is the evaluation of the switch off during the voltage drop, and we are doing this by controlling this load here. So if the DC voltage C of the capacitance is bigger than a specific threshold, then the load resistance is controlled to consume constant power, and otherwise if the load voltage drops this threshold, then it becomes infinite, and so no power is drawn from the grid. The general component design here is that it's normally according to the hold-up time and especially harmonic requirements. This is why we have these different PFC techniques. But here we set these components manual to meet the power response. But if you want to have more information how these circuits are designed, then you can have a look in the paper. Now, one of the main results of the paper is a comparison between the measurements and the simulations results. So we have in gray the measurements and in red the simulations. Now it's a little bit maybe hard to see here to distinguish between them, but maybe as you can see here, these lines overlap. more or less, and this is here for 20%. Now, if we increase the voltage drop for 40, 60, 80, and 100%, then we see that in general, especially here for the first load, the reactive power, so the match is really, really good. We have here a slight mismatch for the active power, which is also reflected here at the peak value. For the second load, we have a greater mismatch here for the reactive power, but this is also a little bit of the limitation of the amplifiers. The voltage was not as big distorted as for the three-phase load, but it was still, the limit was hit, and this is why we think that there is the main deviation here. For the active power, for the load with active power factor correction, we see that the simulation, so the power restoration, is not as fast as for the measurements. We think that this is due to the controller, because we didn't know exactly how the boost converter stage was controlled, and there we implemented an own control, but we couldn't achieve such high restorations here, and also we don't see these oscillations. But in general, it's quite similar. Now, for the three-phase load, as already mentioned, there are greater mismatches between the simulation and the measurements due to the power amplifiers, but we see here before the voltage recovery that we have a quite good match here for active and reactive power. So now that we have these models, I wanted to show you where you can use them. So therefore, we did a test case and want to show you the impact on short-term voltage stability. Therefore, we set up this small test system here, and especially also we want to compare it against a constant power load here. So what you can see here now is for the first scenario, so in red, that's for the constant power load, that in general it's quite similar, but we can see some smaller difference. For example, for the second load, we see that here the voltage during the fault is slightly higher. This is because of its disconnection during the fault, but also we see for the first and the third load that the voltage is here lower, and this is also because of the fast power restoration, and it's slight, it's overshoot. Then for the second scenario, we decreased the short circuit impedance to 1 ohm, and now we see that the constant power load was unstable here, which you can see here by which are more or less numerical errors. And but what's also very interesting to see is that every other power electronic load was stable, or the grid was stable. And we also see here that for the second and fourth load, they're disconnected here. So we have this more or less higher voltage here, and for the first and third load, the voltage was a little bit lower. Now to increase or stress the system a little bit more, we had also a third scenario. So we omitted here the constant power load because it was already unstable. But what we can see here now, that for the second and fourth load, so the grid is stable here. We have quite high voltage due to the disconnection, and the grid but is unstable for the first load because it tries to draw too much power beyond the capabilities of the grid. And what we see for the third load is that we have here a clear delay of voltage recovery, which could also may arise some problems with protection equipment. So now to conclude my presentation, so what we have seen is that the load dynamics we saw in the laboratory has mainly 3 states, so the power reduction, then the restoration, and afterwards the high power consumption, which are here. So the individual dynamics are dependent on the PFC technique. Then we derived some suitable models where we identified, okay, how we have to design those circuits, but I think there's still some potential in the parameter design, so we can match the measurements a little bit better. And then what the test case showed is that the power electronic loads are much more positive than the constant PQ load due to their disconnection and their really power reduction, even if they don't disconnect. So, but there are still some open questions here. So on the one hand, there are still other power electronic loads like electric vehicle chargers, LED, or adjustable speed drives who have to be measured and their dynamics has to be determined. And what is also very interesting, or is also very hard, is to derive common load parameters for these loads. So maybe we have to measure many loads so that we can derive some common load parameters for bigger stability investigations. And also how to aggregate these loads for higher voltage levels, because actually these are low voltage loads, and it's also a big question how to aggregate them so that we can use them in transmission system studies. And maybe it's also possible maybe to have one load which could represent a mix of different PFC techniques. Yes, and that's from my side, and thank you very much for your attention.
Thank you very much, Sebastian. Questions?
Ian Hiskins, University of Michigan. If you go back a slide, the case where you've got constant power and it's jumping all around, I think, no.
You mean this?
That one. Oh, well, that one will do. I think you'll find it's not instability, it's numerical issues associated with algebraic singularity. When you have constant power, you can enter into a region where there are no solutions. And what you're seeing there is numerical error.
Yeah, yes.
It's not, but that's different to stability. This stability is a phenomenon that actually exists. This is just a numerical artifact. That would be my...
Yes, that's okay. That's just, yeah, you're right.
Thank you. Maybe one more question.
Hi, Panos Papadopoulos, University of Strathclyde. So just a clarification question about the derivation of the parameters that you then used in your study. So how did you actually derive the parameters that you then used in this test case that you saw here?
Yes, so first I oriented at other work from other researchers, so I also derived some common load parameters, and we also had these loads, so we can look into them and see which parameters are in there. But it was not possible for every load, and also it was a little bit of try and error. That's
okay. So some manual maybe process that you followed, right?
Please.
So some manual process maybe you followed there.
Yes.
Right. Okay. Yeah. Okay. That's it. Yeah. Thank you.
Thank you very much. So our next paper is called Droop E, exponential droop as a function of power output for grid-forming inverters with autonomous power sharing. Our presenter is Rick Valaskanian. Rick, the floor is yours.
Thank you very much. Well, it's the last session of the symposium. It's good to see so many of you here, certainly a few missing, but thanks for bearing with us. For those of you who I haven't met thus far, I'm Wallace. I just finished up at the University of Colorado Boulder about a month ago. My advisor, Brian Matthias Hodge, is up here. Matt Bossart is also a colleague up there. Amir couldn't make it to IREP, but he's a co-author on this paper. I guess I should probably launch the presentation, huh? How do I even do that? Down here, right? Cool. Okay. So, really, we're going to talk about grid-forming inverters and sort of, creative things that we can do. So the grid-forming inverter, of course, is commanded to adjust the frequency of the output of the device after it serves power, right? So it's maintaining some local voltage phasor, and on an AC power system, when there's a perturbation, that means power is extracted from the device, and then it changes its frequency according to some, in this case, we're looking at droop-controlled GFM inverters, so it does it to maintain synchronicity with other devices. Now, I personally think that this is a very incredible thing that you can do on power systems, that you could directly regulate frequency. And we're going to talk about interesting things you could do to change that. So I'm not going to belabor how frequency works with synchronous generators. Everyone knows. But suffice it to say that if there's an imbalance between mechanical and electrical power, the frequency, you'll get a change in frequency, right? The machine will slow down or speed up. And then you'll have a governor that will change the amount of mechanical power that's supplied to the turbine based on what the droop gain is over here. So notice that D is the droop gain. Keep in mind it's in the denominator. That's important. Typically we set D to be some static value across power systems, and this allows us to get power sharing amongst all of these frequency responsive devices. So it makes a lot of sense. With the grid forming inverter, in particular the droop controlled one, so we're not talking about virtual synchronous machines, a virtual oscillator control. This is just strict, it's technically multi-loop droop, right? So in this case, what you do is you have a power set point, and then when the amount of power that's coming out of the device changes, you change the frequency according to what the droop gain is. So again, D. Notice that if you derive the rate of change of frequency equation for the GFM inverter, D is also proportional to rock-off for the GFM inverter. So that's a good thing to keep in mind. Yeah, okay. So really, when you notice that D for synchronous generators in the denominator, clearly we can't change that too much. We certainly can't make it close to 0 or 1. We ran, obviously, you can run simulations and you see that it goes unstable. We're not going to show that. But because D is in the numerator for the GFM, at least in theory, you could kind of make it whatever you want, right? So that really kind of brings us to the droop E concept. I would say that droop E is the title we came on because it's exponential droop, and we just wanted to be a little cheeky, so we called it droop E for fun. So really, the kernel of the idea is if you have a grid-forming inverter that's at some lower dispatch level, which is to say there's a large amount of available headroom. Now, this is a condition that you may find battery energy storage systems operate in near future conditions. I was actually inspired to do this based on dispatch scenarios from the Maui power system, where we were looking at future cases where there would be batteries online and they're basically just idling on the system. So why couldn't we then operate with a smaller D value? Now that alone is not a novel thing, but we do know that that would deliver more power to the network with a smaller frequency deviation. Again, if you want to deliver more power in an AC system, when you're regulating frequency, what do? You just don't change your frequency as much, right? So an added benefit, again, remember that D is proportional to rock-off, is that rock-off becomes smaller. So that's cool. But we wouldn't want this to just be a static D value, right? Because then we're going to be slamming into our limits as we start to deliver more power. So D should grow as dispatch increases or as the device is serving more power, right? So we get natural limiting, we don't bump into our limits. So that really comes to the kernel of the idea. And that is, instead of setting D to be some static value, it's like, why don't we make D a function of the power output of the grid-forming device, right? So this is more or less the equation. Omega B is, of course, the base frequency. Alpha and beta here are shaping parameters for the exponential function. We're all pretty familiar with those. Of course, the first value within the brackets is going to be static based on the power set point. But then the second one will change, and that is what will change the D value as the device is delivering power or based on what the dispatch is. So just to have a view of what's actually going on here, so this is sort of a frequency versus power output plot of two operating conditions, two droop E curves, and also one static one. So the first one is the static, and it's this mustard line. You can see it's linear, so it's at 5%, right? And really the idea here is you're at 0.2 per unit, right? That's what your GFM device is dispatched at. And imagine that there's a perturbation on the system, and the device delivers. How much does it deliver? It delivers 0.33 per unit of power. And at that point, it slams into this line here, which I'm calling its UFLS potential, so under frequency load shed. I would highlight that this is something that will change from system to system, and different operators will have different conditions. Certainly in Europe, it would be very different. But the thing that was really bothering me is that the GFM device would only deliver a third of its available power before it got to some frequency level that we didn't think was actually appropriate, right? So it's like, well, what about the other 0.5 per unit of power that remains, especially when you have a device that could say, deliver that power without even having to actually react to anything. So it's not reacting to a change in frequency, right? So that's when you take the droopy curve. And so we have alpha and beta here. Alpha is 0.002 and beta is 3. I would highlight that those were not rigorously chosen, besides just sort of doing a little bit of graphical analysis to see which curve we like the most. There's a whole world of opportunity to optimize those. We'll talk more about that shortly. But you can see that if you had this droopy device dispatched at 0.2 per unit, so the tangent at that point is 1%, so we're getting the larger or the smaller D value, right? But then as it's delivering more power, D is changing, so it is dropping its frequency. And by the time it would get to that 59 hertz UFLS point that we're saying, you would actually deliver a quarter more power to the network. So that's pretty cool, right? And then if you look at the other dispatch point, so this is 0.73. I chose that one because at this point, that's where the slope is related, that's equitable to what 5% static would be. You can see, it is starting to tail down and shoot down faster, so D is becoming larger at the higher dispatch. So that's sort of what's going on here. So as one does when you have a new control thing, you have to do a little small signal stability analysis. So I'm not going to spend too much time on this because the time domain simulations are a lot more interesting. But suffice it to say that we took the sour machine, machine 3. We had the governor model, so it's a 9th order. And then for this study, we assumed that it was a constant output voltage for the GFM. There had been precedent in other analyses of droop gains on GFM, so we just grabbed that for simplicity. I think in a more rigorous analysis in the future, you would use the whole 15th order plus all of the extra things in the GFM. But for now, we're just going to take this 3-bus model. So bus 1 is an SG, synchronous generator, excuse me. It's 100 MVA. Bus 3 is a grid forming inverter. It's 50 MVA. There's a load right in the middle. The impedances are equal, so electrically the same distance. You linearize your DEAs, of course, and then down here we have this block diagram. That's basically the frequency control of the grid forming device. So you have measured power, you filter it, and then you use that filtered power to decide what your droop should go to. And then you add your frequency set point, and then you have your frequency for your device. So what we're going to do is we vary the dispatch of the grid forming inverter from very, very low, so nearly 0 when D would be very small, all the way up to 1, where D would presumably be quite large. Again, not going to belabor these. We really just the primary takeaway here is that, as one wants in a small signal stability analysis, all of the negative values are, all of the real parts are negative, excuse me. There is sort of a curious bifurcation going on here. So these are the eigenvalues of the system that have participating states from the grid forming inverter. There are certainly other ones, but they weren't necessarily of interest because they were the synchronous generator exclusive participating parameters. So really, the bifurcation is curious. We didn't analyze that too much here. It would be curious to dig more into that to see what's going on. So we presume that it is stable in this 3-bus system based on the small signal stability. So we're going to move on and do simulations in the electromagnetic transient domain. So I've done a lot of work in PSCAD. This is actually, you could call it a 4-order grid forming inverter that's available open source if anyone wants it. So it has the power controller, the voltage controller, the current controller. There's current limiting. There's the DC side system, which is assuming a 0th order battery, and then it's just a buck boost converter. And we're taking the capacitor size that's equal to what would be 1 electrical cycle of rated output, which is sort of on par with what you would expect with a grid forming inverter. The SG model, again, it includes sort of the basic exciter governor from the Sour Pi 9-bus. And to highlight, this is machine 3, if you go to chapter 6 and 7. Great, so we're going to do simulations on that 3-bus system. We're doing a 10% load step. And so what you have over here is case A is on the left. Case A is where the GFM inverter is dispatched at 5%, right? So again, D is going to be quite smaller at that point. And what we're looking at in the upper left pane here, so there is going to be a blue trace and a green dotted trace. Those are both the results of the EMT simulation. And then that black dotted one is actually a different simulation where it's only 5% static, right? So those are 2 different ones. So naturally, you would expect the blue and green ones to more or less align because they're on the same system. It's obvious that the frequency doesn't change nearly as much. And that becomes obvious why when you look at the power output of the 2 devices. So you can see the grid forming inverter, again, the green trace line, is delivering a lot more power than the synchronous generator, which is exactly what we wanted. We're just telling it to not change its frequency as much. Case B, so if that's the GFM is dispatched at 50%, it's not going to keep the frequency as close to the nominal because that's the whole idea is that it's not supplying as much power as it had been at the lower dispatch. But you can still see that it is an improvement over the static value. Things get a little complicated and potentially problematic when you go to case C, which is where the dispatch is 0.95. You can see that there are these oscillations that are happening. Of course, the GFM device is not delivering as much power because it's near its limit, and that's the whole idea, is that it's not going to hit the limits. And the frequency ends up being lower in the 5% static case. And this would be expected because actually in the 5% static case, because we're not doing power limiting, it actually would violate its power limits. Something we didn't investigate, as it was a newer idea since doing the publication, is that we could just put a ceiling on D, because we know in GFM inverters that if D becomes too large, you do get oscillations. So we could just take the tangent of the curve on that exponential at some point and say, we're too close to our limits, just hang out right there. So the astute listener will be like, well, we don't have power sharing if we do this because we're not only doing 5% static, right? Which is kind of the whole idea of doing 5% in the first place. It's a great point. We had to figure that out. So we came up with this power sharing controller, right? So essentially what this does is it takes the output of the GFM inverter, so PM, it compares it to the set point, and what you do is you calculate what the frequency would be had you been operating at a 5% droop, right? And then what you do is you compare that to what the actual output is. So this is this omega D value here. You get an error, and when the device registers that there's been a deviation in power output, and B, that the transients have died out, that logic block will close, and then you pass that error through an integrator, and you end up with this omega PS. And you add that to the actual output here of the exponential function. And what this does is it allows the frequency to track to the point where it would actually achieve power sharing. Now, I should highlight that you could set D 5% literally to whatever you wanted. You could do 4% or 3% or anything. But one thing that we did learn is that it's very important to make sure that you keep this droopulation in line with the system because it's required for stability. You won't, like if you explicitly regulate frequency to some value you want, you're going to end up with problems. You have to have the droop characteristics to keep things synchronized. So, epsilon P, epsilon dP, and K, those are tunable parameters. Not shown is that the logic block is actually going to open upon meeting some sort of convergence criteria that you may have. So, does it work? Well, so we did it in the 3-bus system. We did a very large load step just for fun to really shock the system. And you can see we've got the blue trace here, which is the droopy curve. And then the magenta one is the 5% static. So those are 2 different simulations. We did the large load perturbation to show that even with the 5%, you would actually hit that, sort of the arbitrary UFLS point, but a pretty low frequency nonetheless. And you can see that the droopy, it's a much more desirable frequency response because it's less deviant. But the really cool thing is that right around 6 seconds, that's when the device registers that there's been a change in power and that the transients have died out. And then the power sharing controller kicks in, the frequency lowers, and it arrives at that value that you would have gotten had it been at 5%. Same deal with the GFM device power. We know it's going to supply more, it does, and then at 6 seconds, it ends up converging at this 5% point. Just to give you an idea of what's actually going on, you can see this blue trace here. That's the frequency output. It's this one right here. But you can see what's going on. We have, you got this orange curve here. That's the calculated 5%. And then when the logic block closes, that's when it starts to compare that to this blue trace here. And then you get this correction factor, this green. And you can actually tease out from these responses why it's important to keep this in line, because this value here, omega DE, actually changes as you're adding this frequency offset. So of course, we did it on a 3-bus system. Is it going to work if there are multiple droopy devices working on a larger system? Spoiler alert, yes. So we did it on the 39-bus system. Most of you are familiar with this 10-bus system. We had all these devices rated at 1,000 MVA. As all synchronous generators, they're all the machine 3 from Sauer again. And what we did is we ran 3 cases. 39A is all synchronous generators. 39B is where we trade out generator 0, generator 4, and generator 8, which are labeled with static 5%. And then case 39C is where we do it with the droop E inverters. And the perturbation that we did, we just tripped generator 7 offline. That equates to about a 8.5% generation loss. So, and then we're going to look at the weighted average frequency. And so it does work. You sort of get the response you would expect with case 39A, your standard synchronous generator, oscillations, low nadir, all of that good stuff. It's better with the static case, 39B. You can see the nadir is higher. We know that it adds damping to the system. But then with 39C, when you have all these, those 3 GFM inverters operating as Droop E devices, you can see that it is even less deviant. In fact, the nadir of that case is the settling frequency, which you get to. You can see that the devices start to do the autonomous power sharing at around 6 seconds. Something that is fun to note is that the inertia in 39A with all the synchronous generators is 3 seconds. And the inertia in 39C with the 3 GFM inverters is 2.1 seconds. And yet, with this Droop E thing going on, you end up having the same rock-off because you had one of those devices that was at a much lower dispatch. So we really utilized that headroom in that case. And then finally, if you look at the device active power, you can tease out that these are actually being triggered autonomously. You have generator 8 starts before 4, which starts before 0, and then they all start to converge to that point of equitable power sharing. Now, of course, generator 9 is governor limited. That's why it's not actually doing anything. So yeah, that's cool. So in conclusion, we sort of like came across this fun idea of doing exponential droop as a function of power output. We like to call it droopy because it's fun. It seems to be a stable frequency control approach, and it seems to yield an improved frequency response over the static response. And of course, after you get this unequitable power sharing with the initial transient response, we came up with this power sharing controller so that you can arrive at the 5% value or whatever else you would want to get to. And I'm probably giving away too many things to work on here, but these are a lot of the thoughts that I've been having. Can the high dispatch oscillations be mitigated with the limit on D? Probably. Really, the big one, honestly, like, are there other nonlinear functions that would be more beneficial, like power laws or polynomials? Can the shaping parameters of the exponential function be tuned for optimality and or some sort of preferred response at different times? You can imagine a system operator tweaking those things to get sort of the transient responses that they might desire. One thing that I also find compelling, you think about frequency response obligation and how much power you get from a synchronous generator based on a frequency deviation, right? And that's sort of set based on the size of the generator, and just at that point it's sort of discretized in the sense that you have to have the frequency deviation to get power out of the device. If you actually had lower dispatch GFM devices, then you might get away with having fewer devices. That could be an interesting thing from an economic perspective. Naturally, fault response, right? That's a pretty big deal. We didn't look at that at all, but that would definitely be something to look into. And finally, it's one of the fun things with this autonomous power sharing controller. It's sort of like, if you can sort of arrive to whatever frequency you need to a few seconds after your transient, then what's the point in ever doing a static droop gain with a GFM inverter? Like, how could we get a little quirky and have some more fun? So yeah, that's pretty much it. Thank you very much. Yeah.
Question, Sakis?
Yeah.
Excellent presentation. I enjoyed it. One question is that in the simulations you did, was it full EMTP type analysis with switching and so on? Because it looked to me that the responses are very fast. And if you drive an inverter at these fast responses, then you run the possibility of misfirings and so on. So in other words, the controls are fast, but may not be as fast as what you show here. So the question is feasibility of this issue, because it looks like the inverter is driven to very fast changes.
Right. Yeah, that's a great question. Yeah, so it is full EMT of synchronous generators, but also the GFM. So this is it's a 15th order model at its core, and then we also have the DC side dynamics. We had looked into, so in this case it's a DC buck boost converter, which is sized again with this sort of capacitor rating of a 1 electrical cycle, which based on conversations with power electronics folks, they appreciated that as an okay size. And then we had looked into having higher order batteries sitting on the downstream side of the DC buck boost converter, and ended up just using the 0th order because we didn't find that the higher order models really impacted it, but we did a lot of sensitivities on that. So it is full order in the sense that we're not doing PWM and switching, so we're using average switching, but otherwise it's pretty high order. Sure.
Claudio Canizares, University of Waterloo. My question goes back to when you have multiple of these converters.
Yeah.
In microgrids, we have observed that, which I think will apply to this, when you have multiple converters, the groups are very important because might make your system unstable because of oscillations between converter controls, particularly current controls. And in that case, you might have, we've seen this, and it creates an instabilities. And the more converters you have, the more the problem. So I wonder whether you have looked at that problem. That would be interesting because maybe you're able, with this variable group control, one that is stable, unstable might make it stable. Going back to your idea that maybe you don't need a fixed group.
Right, right. Yeah, we hadn't dug too deep into it. It is really interesting to think, though, that we have these 3 GFM inverters that are at different dispatches, so they are actually at different static values in steady state. Of course, these were EMT simulations, so we had to bring the simulation to steady state so we didn't have oscillation issues in getting there. Oh, I see. We didn't observe them in these simulations, but it...
No, maybe not, but what I'm...
Huh?
Maybe not, but as you move forward with this, or as somebody else moves forward with this, I think it would be interesting to see when you have that problem, because it happens, whether this would solve that problem.
Got you. And that would be like an alpha-beta tuning thing on the exponential.
Yeah, it would
in a way,
be better
right?
than, because you have this variable group, maybe that eliminates that problem. That
Right.
would be interesting to see. That was all was.
No, that's really interesting. Thank you.
It's okay, Maria. Yes, because that's a clarification.
Okay.
Sorry, I just had a clarification
Sure.
question. You start from the droop as the basic notion. How are you going to go from your back-boost model to the droop? You just assume that you can tune the droop from outside, but actually there has to be, changing in logic of the inverter control to get that droop. So, and that is $1 million question in these things, because I think what's going to happen at the end, as you adjust these droops, you have to have more adaptive primary control on the book, on the back boost. And we have some experience with that on tactical microgrids, but I think the fundamental question that I have is, and the community does it all the time, you assume that you can tune the droop from the outside. That is not true.
Right, yeah, no, this would very much be a, ABB or Tesla is like, all right, we're going to install exponential droop on our inverter, which is going to allow us to change, like they would clearly have to be a part of that, right? Does that answer your question? No.
It doesn't, and it's a very important one, I think, because you assume your starting problem formulation is that you can somehow tweak the parameters on the droop.
Right. I guess
and that is half of the job. And I think that Saki's question had to do a little bit with that. Are you going to have internal instabilities, through switching, or what I talked about a couple of nights ago is how do you make this internal control more adaptive to actually create maybe even the droop on the interface and so forth. So I don't think that's an easy job before you implement this.
Yeah, I agree. I don't think it would be easy at all. But at the same time, I do, if a manufacturer created a grid-forming inverter that was doing droop control, they would manually set it to be 5%. So I don't think it would be a huge stretch for them to set it to an exponential function as opposed to a static value. But you would certainly need them online, right? Yeah. Okay.
Great, thank you very much, Alan. All right, so our last paper now. The last paper is titled Data-Driven Fast Frequency Control Using Inverter-Based Resources, and our presenter is Etinosa. Okay, sure. Okay.
Good afternoon. Good afternoon, everyone. It's Nusai Koren, a PhD student at the University of Waterloo. We're presenting our work on data-driven fast frequency control using inverter-based resources. I'd like to acknowledge my supervisor, Professor John Simpson-Poko, and our collaborators. And our collaborators from EPRI, Evangelos, Mahindra, Abitalib, and Lynn. So the structure of the talk will start by motivating the problem, and we'll give a brief overview of our proposed frequency control framework from our previous work. And then the main contribution of this work is extending that work to make it completely data-driven. And then we'll present simulation result that validates our approach, and we'll end by briefly recapping what we have done so far. And to start with the motivation, there's a growing trend in grid modernization. You have newer inverter-based resources replacing fossil fuel-powered synchronous generators. Also, there is a growing need to improve grid visibility, which is resulting in improvement in the communication and monitoring architecture in the system. However, this modernization actually bringing up new challenges, especially with the increased penetration of inverter-based resources. For example, we have reduced system inertia, increased net load variability due to the intermittent sources of the IBRs, and this is resulting in far faster frequency dynamics compared to traditional grids. Also, a new challenge has been noted in the literature. It's the problem of regional variation in frequency profile due to spatially heterogeneous frequency characteristics, which is coming up in grids where you have some areas with relatively high penetration of renewable resources as compared to other areas. And we can envisage in future grids where we have increasing clusters such as that, and also in situations where even those heterogeneous characteristics could become time varying due to the relative dispatch of IBR resources versus conventional units in those clusters. And this motivates the need for fast and localized frequency control in order to prevent inadvertent tripping of protection devices. However, it's not all doom. We have an opportunity to utilize this improved communication architecture and fast-acting devices to enable fast frequency control using IBRs. Like we stated on the previous slide, due to these new challenges, faster frequency dynamics and heterogeneous frequency characteristics, it may render some of the conventional frequency control strategies ineffective, and there's a need to come up with new control frameworks. And in our previous work, we proposed one of such frameworks, which has these main characteristics, which has a hierarchical, fast, and localized frequency control. And also it has this attribute of trying to preserve simplicity in design by minimizing our model information requirements. In this work, our main contribution from this paper is to extend our previous work by making the framework to be completely data-driven. And this is, I just give a brief overview of our proposed control framework from our previous work. Starting point, it's giving a grid. We divide the grid into smaller geographical regions, which we call local control areas. And in those local control areas, we're able to, the main point in these smaller areas is to be able to quickly estimate and compensate for local imbalances arising in those areas. And also, since we divide the system into smaller areas, we're able to consider the unique frequency characteristics of those areas and take it into consideration in closing our control loop. Also, we have, in our system, we have two main layers. The local control, the local layer is the control loop in this small local control areas we have divided our system into. And then we have a higher coordinating layer, which is activated in situations where we have more severe contingencies and the resources in each area is not able to compensate for that. We have more details about our global loop, in which we design an iterative scheme to preserve privacy and other details, which you could find in this paper, but in this talk we focus on the local control loop. In a local control loop, like we said previously, the main philosophy is to quickly estimate and compensate for all local active power imbalance in the system. And in order for us to do that, we use a measurement of the frequency, measurement of the timeline deviation and IVRs, combined with a nominal model of the local area to design an estimator that provides real-time estimate of the local imbalance in that system. And then we use the value of that estimate to run it through an optimal power allocation scheme and use it to dispatch the IBRs in order to compensate for that imbalance. Also, more details on the power allocation algorithm and how we design our system in order to better tolerate communication delays can be found in our previous paper. But in this note, in this present talk, we focus on the disturbance estimator design, because this is the only component that requires model information for its operation. So from our previous work in designing a disturbance estimator, we use an aggregate model of the LCA, which has the equation for the governor turbine system and the swing equation. We discretize and convert that equation into state space form. And then we model the unmeasurable disturbance using a constant disturbance model from box 2. And when we combine and augment these two systems, we get the system in 3. And then we could use traditional control tools to design either a Kalmar-based filter or a Omega type estimator based on this augmented system. And then we use the real-time estimate and feed it back to the power allocation algorithm. But as the power system is increasing in size and getting more complex, it may not be so easy to get accurate parameters for our parameterized model of the system. So we try to remove that requirement and get a fully measurement-based implementation of the disturbance estimator. So to that end, we leverage insights from behavioral systems theory, and we have more details on the full form of this paper, but in this presentation, we focus on just the key steps that we need to get data-driven estimator. So the first step is we collect historical, offline we collect historical input-output data for the system. We pair that with real-time measurements during operation of past data of the system. We use both the historical collected data and the real-time measurement data to form a prediction of the frequency deviation of the system, the local control area. We compare that prediction with the actual measured frequency deviation, and we use that in a correction step to update the disturbance estimate in order to drive it to desired value, which matches with the current active power imbalance in that system. In applying our update rule, our parameter L there, it's also obtained by using the same offline data we have collected from the first step. And something that is worth noting is that we have a single tunable parameters in order to modify the performance of this control loop. So if the value epsilon naught is used to modify the system response in terms of both oscillation and settling time. Next, we show a simulation result to validate our approach. The first test system we are considering is 3 copies of the IEEE NIBOS system, where we have added additional 2 IBRs to each area. And in this simulation, we are considering just a step load change in bus 8. And I'll try to draw your attention to the second plot, the lower plot. After the disturbance is added to the system at about 10 seconds, we can see that for using both approach, both the data-driven approach and model-based approach, we get relatively fast and accurate estimate of the local imbalance in the system. And then that value is plugged into the power allocation to be dispatched the IBROs. And we can see from the top plot, in terms of the frequency response, we can see a very fast and non-oscillatory response in the system response. Also, we'd like to note that despite using just measurement-based systems, despite using just measurements in disturbance estimator design, a data-driven approach actually slightly outperforms a model-based approach. Now to a more realistic system, a bigger IEEE 68-ball system. We have used the same ideas. We're subdividing the system into 5 areas and added IBRs, 2 IBRs in each of those areas. And we are still considering the same step load change response in bus 33. And similarly to the previous scenario, we have similar observations that using a data-driven approach slightly outperforms a model-based approach, and we don't see a worse performance by replacing a model-based approach. This is also consistent with the disturbance estimates using both approaches. So to recap, we have proposed an approach, a frequency control approach, which is which provides fast and localized frequency control using inverter-based resources. We have tried in this work to replace our model-based disturbance estimator design from our previous work with a purely data-driven approach. And from our results, we can see that our performance using the data-based approach, it's comparable to using the model-based approach. I also like to note that despite showing just step changes in this work, in the fuller paper, we have also considered other contingencies such as generator trips and three-phase to ground fault, and we see similar performance with what we have shown. In terms of future work, so we are looking into extending and getting better estimation or disturbance update rules for our disturbance, for correction step in our disturbance estimate formulation by moving into a moving horizon disturbance estimation framework. Also, we are thinking of adding a coordination between transmission and distribution system by actually able to dispatch some of the resources connected in the distribution layer. Thank you.
Any questions? Helio?
Apologize for a trivial question. Now, I'm just curious why both models, the small model and the large model, has the other two systems showing opposite results between the model-based and the measurement-based. So, this one, so you can see that the dashed line, if you look at the bottom one, it's not critical because the most important area is good, right? But I'm just curious, why is the no event area always give you an opposite response between the model and the data-driven case? Because your data is from the model, supposedly you don't model, but you use generated data from the model. So I was expecting to have the little small peaks line up, but they happen to be opposite.
Yeah, thanks for that question. In reality, okay, we don't have a plot now, but we actually try to validate the plot using, we are using a very simple model, like a two-order model for the model-based design. And it's not really so accurate in terms of getting the nonlinear performance of the system. So we hypothesize that our data-driven measurements has actually better captures the dynamics of those areas. So the model-based plot you're seeing, it's actually a very simplified model of the area, which does not, in open simulation, does not accurately tally with the nonlinear performance of the system. So the database response gives us, because we have higher, we're able to capture higher dynamics, which gives us a more accurate response.
So in this case, for those bottom curves, we should believe the data-driven model because the model has been simplified.
Yeah.
Okay, thank you.
Thank you.
All right, thank you very much. I will next invite all of our speakers to come up front, and Stephen will lead the discussion.
Well, thank you all the speakers, and thank you all audience, everyone's still here. That's fantastic. Claudio, yes, please go ahead. Claudio and then Yilu.
To close the conference asking more questions. I had a question for Sebastian. I found it quite interesting and relevant that you're looking at this behavior of these loads. However, over lunch, I guess Misha is not here. Over lunch, we were discussing the effect of aggregation, right? And when you look at these, individually the loads behave in a certain way. You presented here, and I think that's valid work, important work, in fact. When you aggregate these loads, for example, to give you an example of a distribution feeder, each individual load behaves very weird. When you add them up, they have some certain behavior different from what you expect individually. So I was wondering whether you have thought about it or looked at the issue of what if you start aggregating these different loads, and what would you see from the system side, right, as opposed to the individual side? That was my first question. My second question is whether, with all these LEDs, would any of these loads would match that kind of system you have in LEDs that will represent the possible behavior, dynamic behavior of these loads? Thank you.
I see. Yeah, now it's working. Perfect. Yeah, according to the first question, yeah, it's very important question. It's not so easy to answer because so yeah, okay, from a system perspective, of course you would see this reduction in power. So what I said is with these three main states. That's also what I want to highlight with the paper, that also they are different, or they have different dynamics. You can, they have similar dynamics. Not exactly the same, but a little bit similar. And yeah, for modeling, what you could do is that you are also like other composite loads that you maybe distinguish between the different PFC techniques, because it's, in my opinion, the biggest difference. Besides which is either is it for one phase or three phase. It's also another issue. Then for the LEDs, I know there are some works. It's also from the papers the paper that I mentioned in my paper. Yes, they are similar. They could also disconnect. But I don't know if they are really exactly like these switch mode power supplies. I think they're a little bit different.
That would be interesting to see.
But now I remember they could also have a similar equivalent circuit, but then the resistance. So also I had these controlled load resistance. So normally you have a boost or a buck converter that tries to control the DC voltage at the actual load. And because it is so fast, you can assume that there is a constant load. There's also a simplification there. But I know that for LED devices, this is also something special how this simplified load is controlled.
Ilu, please.
I have a question related to the exponential droop that was very interesting. My question is, did you run a hardware in the loop or some kind of a real-time testing and to see how it works?
No. Okay, good. We haven't done hardware in the loop testing with it yet. I have been affiliated with NREL for a while, and I was going to try to get them to do that at the Flatirons campus, but we weren't able to do that in time for this conference.
Okay, so, well, let's talk afterwards. I may be able to help, because we have inverters, we have all the control algorithm inside inverters from our industry vendors. So they may be, I'm thinking, we can probably easily input a function, just does the test.
Yeah.
To see, yeah. Now, I wanted to ask a question related to the question Maria asked.
Sure.
Do we need to worry about the interaction between the inner loop and the outer loop as long as the inner loop can satisfy the requirement of the outer loop? Because once that is already met, you can leave the inner loop alone. You know, I know if I have this requirement of power injection at a certain speed, I know that the inner loop can deliver. I'm happy to go ahead, design my outer loop as long as I don't ask more, it's necessary. Wanted to know from both of you, do I understand that correctly?
Yes, please, Mary. Yeah.
Sorry, the reason that I was so loud about that question, I spent 2 years at Lincoln Lab on this question. You know, it actually, if you do constant, you tune the droop once for the range of conditions and droop is linearized, you fix it once to be stable internally and they are okay, right? Now what's happening here with the concept put forward with Droop E, where you go all over rescheduling and going over auto conditions, I think what's going to be needed is to retune or change the logic or have adaptive control logic internally to make sure that the droop that he wants to use at the system level actually is implemented. It's a completely different challenge, I think. And a lot of literature actually just starts with the droop, assuming that that doesn't depend at all on how you control things internally. We can talk about that a little more.
Yeah, we could talk offline.
Okay.
I do think that from the timescale separation perspective, though, if you, I think what you're getting at is if the inner voltage and current controllers are operating sufficiently quickly, then you can sort of get away with it.
Report which says it's not.
Okay, so it's 2 to 1, right?
Oh. All right. We'll take it offline.
Yeah, no, I think. Yeah, I think it's a wonderful thing if the conference results in the concrete collaborations that will be reported in the next IRAP. Okay.
I was thinking about that. That's great.
Yeah. Great. Yes, please, Costas. Oh, sorry, Rodrigo first. Oh, okay. And then Rodrigo.
Costas Vournas, National Technical University of Athens in Greece. I have two observations and maybe comments that you can answer. Concerning the variable droop, what you are doing is, I think, is commendable. It is somewhat similar to what the hydro units governor does. In the hydro unit, you want to have slow response initially, so large droop, and then switch with an exponential function, but through a transfer function, to load droop. Now, what you do is you want your, if I understand well, you want your converter, suppose that you have a battery behind, otherwise you don't have any energy to give, to respond fast, but then back up so that it does not consume all the battery. So in this case, you should start with a low droop, high gain, and then go back to, so you can, instead of, directly deciding on the exponential, you can, maybe in power electronics, it's more easy to do a transfer function. So this is just a suggestion if you want to comment on this.
Yeah, I appreciate the comment. I guess it's certainly, I don't think I ever mentioned that we were certainly assuming that these were battery energy storage systems with grid-forming inverters. So we assumed the energy availability, but we also, the idea with sort of getting to power sharing within a few seconds after the transient was that you wouldn't be overly consuming energy more than any other device. So, and certainly there would be some secondary or tertiary control to get everyone back to set points afterwards.
No, but you can do also by changing the droop as you do, but anyway. So that's the one. The other, I wanted to point out to Sebastian, this case with the constant power load that Ian also referred that maybe not so easy to simulate. I understand that you try to model each separate device or type of devices. Maybe if you take the whole load of a substation or a node in the distribution system, then you certainly will have some form of voltage-dependent load, because all your loads seem to be, for small disturbances, they were returning to constant power. If you had large disturbances, it seems that they could go down. But in any way, they were all constant power. So if in the actual load you have some more soft, let's say, loads, then the overall response would be more reasonable, let's say. Have you thought of that? I mean, taking the whole substation or the whole node as a load?
So if I understand you correctly, if I look from a substation, there are also other loads. Of course, there may be the effect of these loads is not so big. And on the other hand, you're absolutely right. If the voltage change is not that big, then it stays more or less as a constant power load. That's absolutely true. Because the mechanism behind is you have this uncontrolled bridge rectifier. And so if the DC voltage or the rectified voltage is bigger than the grid voltage, then the bridge rectifier blocks the load from the grid. But it depends then really if you can see that maybe in one cycle the voltage is lower or bigger. The DC voltage is bigger than the grid voltage. So and also I think at least in the plus minus 10% range there are really constant power loads. There are actually, there are also some works who derived some steady state models from these power electronic loads, and then you can also see that you have in this plus minus 10% range also some kind of voltage dependency, mainly on the reactive power and a little bit on the active power, but they are really just very voltage unsensitive in this area.
Okay, thank you.
Yeah. Rodrigo, please.
Rodrigo Ramos from the University of São Paulo in Brazil. We have been able to check with our co-authors, with Victor, who made the word of the PhD student. We checked with him, so I would like to give the opportunity of Ada to elaborate a little more on the response to Claudio's question about model validation. And I have a question for Espinosa. I can do, should I?
Yeah, please.
Okay.
You mean, do you want No. Yeah, please, you can respond, and then you ask your second question. Yeah.
Okay.
Great.
Thanks for the opportunity, Rodrigo. So to complement the question about the validation, we checked with Victor, that who did the most part of the work, and he used the data, the data from the Brazilian system is available in the Center for Energy Research in Brazil, and he got the complete system, the data from the complete system, and run power flow and continuation power flow analysis using the complete system and using the Brazilian package software for run this analysis, got the results, and compared with his subsystem, the test system that he proposed. And by comparing, he could validate the complete system with the proposed test system. Thank you.
And the simulation of the large system was done in the CPAL package using the load flow and continuation load flow program that they have, but the validation, the results on the reduced or the test system were produced by PSAT. So they were obtained from MATLAB. So this is a cross-validation on two different software. So my question to Etinosa is, usually the type of disturbances that that lead the system to need frequency control are large disturbances, because for example, the synchronous machines have dead bands, and if the frequency fluctuates but does not leave this dead band, there's no need to control the frequency. So you mentioned that you use a Kalman filter or Leuenberger type estimator. So is this a nonlinear approach, or is it a linear approach to the estimation? And if it's linear, how can you deal with the large perturbations that are the ones where the frequency control is mostly needed?
Hi.
Yep.
So the estimator are linear-based estimators. So that's like the first question. Then in terms of the dead band, especially for the frequency, in getting measurement of the frequency. So some of these measurement of the frequency deviation may not show up too much if you have very small load variations. So we're also looking at not using those measurement of frequency, but in our work we are using the frequency measurement, and also we are using the power deviation in the system, together with a model like that for the first approach, the model-based approach, which you mentioned the Kalman filter. So using the measurement of the frequency, measurement of the tie line deviations, and also the nominal model of the system to estimate the value. So for the region that we are considering, like about, so we are not really trying to correct all the small changes, so because the inverters also have like their droop. So we are targeting like meaningful changes that create a meaningful division in the system, and those are the ones we are trying to like correct.
Yeah. No. Thank you.
Okay.
Great. Any other question?
Good afternoon, Enrique Vera from University of Waterloo. I have a question for Etinosa. I was just wondering if I see that your model is really robust, right? I was just wondering if you tested your model for other type of faults, because three-phase is of course really strong, but it's not that. I think maybe like single-phase to earth could be more realistic, something that's going to happen in real life. So I was just wondering, you did some tests for other type of faults for your model, and see if you have any insights of the response of your model.
Yes, we did other, those do not present in this slide, in the long form paper, we did other tests. We did three-phase fault, three-phase ground fault, and we did a loss of a generator. We did a generator trip. Yeah, and in the previous work, we also did more varied scenarios. So maybe if you look at those papers, you see.
Yeah, I checked. I read your paper. I thought you just did just for three-phase. I don't know if you did like single phase or something like that, for example.
No, we didn't do single phase, just three-phase to ground fault.
Okay, I was just curious. Okay, thank you.
Yeah. Yes, please.
You were comparing, benchmarking your power flow and continuation power flow with the PSCAD, right? What was your experience? Is that because PSCAD is dynamical integration, right, of the using MATLAB, and the other one is just solving algebraic equations. What was your experience with non-convergence on the power flow side, and did you always get the same equilibrium when you compare the two? Can you comment a little bit on that?
On this test system, you mean? Yes. No, on this test system, we didn't compare PSCAD simulation or EMT. Yes, it's static.
So what did you use MATLAB for?
Because PSAT, it runs in MATLAB. Yes, a toolbox from MATLAB.
Did you simulate dynamics or not?
No, so far. No. It's our future work.
Because the reason that I'm asking the question, we're asking the question, we played with our homegrown dynamic simulator, and very often you get all sorts of crazy things, you know. It's power flow doesn't converge, or even if it converges, you do numerical integration of your dynamics and you end up somewhere else. And we know very little about that relationship between creating equilibrium by numerical integration versus just solving our power flow equations. Pitzauer did a paper, who knows, maybe 30 years ago, on the difference between power flow and, you know, Jacobian when you have dynamical equations. And I think that question is coming up now big way. So you are saying that your model gives information about equilibrium only, right? Static.
Yes, for now it's just static.
Great. Any other questions? We still have time, contrary to other sessions. I have a question. I have a specific question, a technical question, and I have a general question. I'm not sure which is more interesting. So I have a question of Internosa. So your data-driven approach, which is, I think, is really nice. If your historical data, so if your system matrices, ABCD matrices, are time invariant, and if your historical data is rich enough, so that essentially if your Hankel matrix is full rank, then everything's fine. You can do your data-driven approach. If your system, however, changes over time very slowly, it may remain linear. It may even become nonlinear, for example. Does your approach have a mechanism to update that, essentially the Hankel matrix, based on the most recent data, for example? Is that automatic?
Yeah, we have the optionality to update the historical data, like events driven, like after let's say there's a certain period of time or after contingency, we could update it in an event driven way, but we don't have, like, we have not had the mechanism to update that in real time, but just like when there's like an event, or yeah, that's when we update the
okay. Yes, John, please.
Yeah, just to comment. So John Simpson, University of Toronto. Another student that I supervised at University of Waterloo looked at something like this, where what happens if the dynamics are slowly time varying. It seems plausible that you could throw away slightly old data and add new data, and it turns out that just doesn't work very well.
Does not work very well.
Yeah, we spent a lot of time and effort thrown at it, couldn't prove anything, couldn't really get great simulation results. So I think it's best to do it by exception. So after a certain amount of time, you decide there's been sufficient drift in the current system compared to the system that generated the previous data, and then you need to re-identify essentially the model by collecting new data.
But is it easy to detect that?
I think you would have to set up some metrics to monitor, and probably there's lots of different choices there. So I don't have a clear answer on that.
Yeah. Okay, great. Thank you. Any other questions? Anyone want to propose anything to discuss, or we can close?
What's your general question?
Oh, okay, sure. I'm not sure. I would be perfectly happy if no one is interested, then we can all go. And so we had a really interesting discussion at lunch a few days ago. Since we have a lot of people here doing wonderful research, some are more abstract, analytical, some work on very real problems and working with industries and so on. So the question is that there's always going to be a gap between theory and practice. So my colleague told me the gap between theory and practice is a lot greater in practice than in theory. So I think the gap is inevitable. It doesn't need to be unhealthy. It often sometimes is, but it doesn't need to be, I think. So what is your experience or your view on what is the right balance, especially, let's say, at universities, because some theory can be just useless, just waste of time. Not only waste of time, but maybe sort of give the wrong impression to the students when they go to the industry. But on the other side, if you ask the industry, what's the most important problem I can help you with, get this data, I have so many data, different formats, write your software so that I can actually combine my data, right? So it's not clear that would be the most important contribution that researchers can make. And therefore, it's always tricky but important to get the right balance, how much we teach and what we teach in university, and perhaps what the industry's role can be in sort of ideally coordinated fashion so that we can nurture both the basic training, the creativity, how to think, as well as the specific knowledge that we can understand the current actual problems and solve them. So I just wonder if anyone has any comment. Yeah. Claudio and Hamed.
Interesting question because Claudio Canesares, University of Waterloo, because this was somewhat discussed already while we were having these debates. The first one was the issue that I started mentioning, how much is all this optimization used in practice, for example, right? How much is our work used in practice? And how utilities are changing their mindset, not with respect to optimization, but with respect to data, and they are more active, they are more interested with all this data, what they can do. That's my observation. However, I can give you an example of all this work. When I started doing all this voltage stability study, and many of us, we proposed these PV curves, and took 10 years for the utilities to actually use them and believe on them. When we started saying, oh, this is bifurcation stuff, and who cares, and this whole theory, useless. Eventually, they adopted. So it takes a lot from where we are, doing all of these, inverter-based controls that, by the way, we have seen already in microgrids. Now they're starting to appear in transmission systems. People are paying more attention. All these electric vehicles it's been around for a while, and all of a sudden utilities are very concerned about this. So it takes some time. There's some lack of time. However, there's some interesting comment that Hamid made, which is what is happening with our students, right? Our students, if you look at utilities, our students are becoming part of the system. More PhDs are being hired. Before, what do you need a PhD for a utility? Now all of a sudden, utilities, that's happening in Ontario, happening in Alberta, and I presume everywhere else, our students with PhDs are starting to show up in utilities. And they are starting to see value because they went through this training, which, by the way, is not useless, because I've had many of my students say, oh, what I learned in your courses, not only my courses, but in many courses is very useful. I am actually applying. I understand what I'm doing. So I think we just need to be patient, maybe I'll be retired by the time I see big changes, but which is not too long from now. But but I think we are in the right path. I like to believe that what we're doing is valuable. My life experience has been that way, so I would say keep up the good work.
Yeah. So we can be patient. Climate doesn't wait. But Hamid.
You wanted more discussions, Stephen. That's on you. Everybody, you could be home sitting in your room. He wanted more discussions. So I'm not. Anyway. Okay, so in theory, there is no difference between theory and practice. But in practice, there is. So the reality is that there will always be a difference between what we do as theory work and what is being implemented. But, and no matter how much time passes, university will always be ahead of the industry. That's very normal. But I think one thing that we can't ignore about what we do as abstract work is we train our students how to solve problems. Even if it's a very abstract problem, how to solve a problem. And that's the lesson that they take and they go to industry and make changes. So I don't think we should undervalue the training that happens during all these abstract and imaginary work. And by the way, we are among the luckiest people, professional people. We get paid to imagine, to play with things. Just go crazy. Sometimes 99% of things that we do are going to stay in shelves, in papers. Okay. But that's a privilege that we can imagine. So let's keep imagining. Let's keep innovating, and the rest is going to come. That's how I see it. Sorry, thank you.
Thank you, Rodrigo and John.
Rodrigo Ramos from the University of São Paulo in Brazil. I think it's kind of a follow-up on Claudio and Hamid's observations. Yes, we can find a good balance between the training and solving actual problems, but we are mostly talking here about PhD works. And because climate doesn't wait, it is a hot topic now. And I see undergrad students coming into the university and wanting to address very complicated problems involving power electronics. And so I think one message we need to convey to them is that they need to learn the basics before they before they try and solve more complex issues, which are the ones that are, the most urgent ones. So we have to be patient. In any sense, my take is that we have to be patient in a sense.
Thanks, Injun. And Spiros.
You know, I was thinking about your question in terms of how engineering education needs to balance practice and theory. And this has kind of changed over time, right? And in the early days, engineering was taught as a matter of practice, how things work and so on. And whereas after the Second World War, the whole thing changed, and we started looking at the fundamentals, teaching the fundamentals, and we expect that people going out would be able to adjust all of those to the practice. Just a personal experience, when China first opened up, and some of us were traveling to, we found that China was still pretty much using the old Soviet model of teaching. You walk through the labs and they were building transformers things like that, which we never do in the US. And of course, they've changed now because they're starting to come up on the same thing. Now, the question is whether that's the good thing or not. Just teaching the fundamentals, because after all, about 85–90% of our undergraduates go directly into industry. And the number of PhDs that we produce, only a few of them go into academia. Most of them have to go into industry. Maybe 30% go into academia and the rest are in industry. So the question is whether our philosophy of teaching, I think I was mentioning to somebody that we haven't hired an assistant professor, a faculty member in our department for the last 10 years who's had any industrial experience whatsoever. So the big thing is, on the one hand, if you look at those disciplines where practice is very, very important, you don't want a neurosurgeon to have had only theory while they're operating on you, right? On the other hand, my mathematics professor friend told me that if he ever found out that what he's working on is being used by somebody for real things, he would have to move his research. But what is the balance? And I think maybe we are coming to the stage where we are moving too far away from all of the technology that is being introduced into society in such a fast way that we may have to recalibrate.
Yeah, it works in practice. The problem is that it doesn't work in theory. Go ahead, Spiros.
Yeah, Spiros from DDU. I fully agree with everybody what they said. There are two things I want to say. The first is that there is this value in training because first of all, people get a solid knowledge of what's happening, so how power systems work, and then they become creative. So we need to have this kind of openness. So when people go to the industry, they're open to new ideas. The second is that we see that in Denmark, we run the risk to actually get run over. So with these artificial energy islands that happen now in Denmark, we are afraid that the industry is going to go ahead of us. So Energinet does not have the time to wait for us to find the solutions, for example, the operator. So we should also be aware that there's also this, and we need to always be keeping in front, because, yeah.
Great. Thank you.
Yes,
please.
I want to say something. Yes, yes, I think that system engineering is something special. Yes. So what means practice in this case is not very clear for me. So it's not the same that you build something, it's more the interaction. So theory is quite useful, and in France we believe that theory is useful to have good practice. So you need to understand what's a bit of convexity, you need to understand that perhaps it's not good to put hybrid stuff everywhere, to have Zeno behavior everywhere. It's good to have small gain, it's good to have anti-aliasing filter. So you need to have all this kind of background to have good practice. So theory could help to have good practice. We believe that. And of course, it's not the very last, perhaps, things that are very interesting, but at least the fundamental thing about convexity, about Shannon theorem or whatever, you need to have something like that to be able to build something that is quite interesting, because if you let the technology, they can build something that could be incredibly complex and nobody will understand, and I'm afraid of that. When I saw the design of the controller for HVDC Link or things like that, they put a lot of hybrid stuff everywhere. There is a lot of switching everywhere. It's impossible to analyze that. It's just impossible. So, and with machine learning, I'm afraid of that. We are creating a lot of complexity, and it will be impossible to analyze such systems. So to understand a bit the complexity and to reduce that, I think it's interesting. So theory can help you to understand that. So this is my conclusion. Yes.
Thank you.
Time to close the session.
Time to close the session. Great. Thank you all. Well, thank you, Stephen. That was a really interesting question and debate. I appreciate it. Does the reason for being of IREP? So welcome that discussion. Thank you very much. Now we have come to an end for our conference. I wanted to thank you all
again for your participation, for your presence, for your discussions. I think I dare to say it was a successful IREP. Lots of interactions, not only technical but social, because that's very important in this context, and that's very much welcome, and the conference is set up in that way, and I think keeps working, keeps delivering, and I'm happy for that. I guess we'll have another in 3 years, and hopefully will be the same. So thank you very much to all, and before you leave, I just wanted to give you a few, I think some of you already have seen the email from Sana about the trip tomorrow, if you are going. But before I say that, before I discuss that, I'll mention that, don't forget that the dinner today is at the breakfast place we have. It's not at the room that we usually have it. So it's, and I believe that will be open before 7. So if you're feeling hungry before then, I think you should be able to just walk in. Now, regarding and I don't know at what time they serve dinner, but it's certainly before 7. Now, the other thing I wanted to mention is reiterate what Sana said, which is the trip tomorrow starts at 8:30, not 8:30, so a little bit more time there. Be there by 8:20, so the buses leave at 8:30. It'll take about 50 minutes to get to Lake Placid. It's not that close, okay? And then the plan is to be, the idea is to be back here by 2, which means we're going to be taking the bus at around 1. So you'll have about 3.5 hours in Lake Placid. I think you'll find it beautiful. It's really a very special place. Beautiful for walking, easy walk around the lake, or more challenging walk around the trails around it. If anyone is interested, I'm going to be going up the hill, so if you want to join us, I'll be glad to guide you. Around the lake is very obvious. Anyway, enjoy. It's a beautiful, beautiful, beautiful Fairmont hotel. There are stores there, so you can buy stuff. Although I think John said that they don't welcome you at the cafe, but
It could be they just don't welcome me.
might have been that. But anyway, so you can be there and enjoy the view and what is being offered. Now, one important thing to remember is that you need to check out, if you're going to the trip, check out before you leave. Okay? We tried to negotiate late checkout, but it didn't work. They didn't want to do that. So we should be checked out by 11, which means if you're leaving for the trip, please check out before you leave, and you can leave your bags there if that's okay with you. The last thing is that you get the lunch, so bring a snack because we're going to be several hours there, but you can always buy stuff at the Fairmont, but you're going to get the lunch box by the time when we get here, 2 p.m., okay? So I think, did I forget anything? No. Okay, guys, thank you very much.